No, that one's just, you can just throw it out, yeah. Bygones. Okay, how did the calculation go? Was it thumbs up? I totally got it. Thumbs down. I have no idea what happened, or thumbs in the middle. Maybe I kind of got it, but I'm not really sure. What do you guys think? Your calculation for this stuff here. Okay, I got some thumbs in the middle. I got some thumbs down. I got some thumbs up. I've got enough people who are kind of like in the middle or thumbs down that we're going to go through it. If you're wondering what the homework is, if you're like just wanting to work ahead, it is pages. This pen was working not 2 seconds ago. What is wrong with it? There we go. The homework is pages 22 to 24, and that's in the blue book. And in the ivory book, pages 108 to 111. Okay? But in the meantime, we are going to go through this calculation. And I'm just going to copy down the data. We had the initial volume of the NaOH. Yep. And that was 2.81 milliliters. We had the final volume of the NaOH, and that was 13.39 milliliters, 13.39 milliliters. And the first question you were asked was, what was the volume of NaOH delivered? Atrin, could you grab the door for us as well? Thank you so much. Okay, so this would be our burette here. And our initial volume was 2.81 milliliters, and our final volume was 13.39 milliliters. How do we find how much was dripped out? What mathematical operation do we need to do? Sorry, you had something, I thought you had your hand up. No, okay, never mind. I'm not going to put you on the spot like that. You're like, no. Okay, it's all good. If we started here and we finished here, how are you going to figure out how much went out? You're going to subtract, yes? You're going to take 13.39. And you're going to subtract 2.81. Okay? And because I'm too lazy to write milliliters twice, I'm going to write milliliters on the outside of my brackets. Okay, and we get 13.39 minus 2.81 is 10.58 milliliters. Okay. So that was question number 1. Question number 2, we are asked to find the moles of H2C2O4. Now we know the volume of H2C2O4 because that was what we measured out in our pipette, right? We had our 10 milliliter pipette. It's really hard to draw volumetric pipettes. Okay, that was our 10 milliliter pipette, so we had 10.00 milliliters. And we know the concentration of the H2C2O4 because we measured out the grams and converted it to mass and divided by moles, and we got 0.0500. Now, anytime we are doing any work with moles, what should we do when we see molar? We should rewrite it as moles over liters. So 0.0500 moles. And when we're doing stoichiometry, we should write that that is moles of H2C2O4 per liter. What should we do with our milliliters? Convert it into liters. So we're going to move our decimal place 1, 2, 3 places to the left, and that's going to be 0.0100 liters. So question number 2 says find the moles of H2C2O4. Can we do that using this information? Do we need a molar mass? No, because we don't have grams, right? There's no grams, so we don't need that. But what we do have is we have liters, which can cancel with liters. Please make your way down to gym 1 now for a presentation. All grade 12 students, please make your way to gym 1 now for a presentation. Okay, so we have liters, and we have liters on the bottom, and we have moles, which is on the top. Oh my gosh, that's going to get us where we need to go. So we take our 0.01000 liters times 0.0500 moles H2C2O4 per liter. We do that calculation and we get, let's see, 0.01 times 0.05 equals 0.000500. The liters cancel and we're left with moles of H2C2O4. So that was finding moles of A, which is our known substance. Next, we want to find moles of B, which is the NaOH. And we're going to start with what we just found, the moles of A, 0.000500 moles of H2C2O4. We don't want moles of H2C2O4. We want moles of NaOH. Where do we get those numbers from when we're converting from moles of one thing into moles of a different substance? That's from our coefficients, from the balanced equation. Okay, so let's go to our balanced equation. It's on the board. For every one H2C2O4, we react 2 NaOHs. So for every one H2C2O4, we react 2 moles of NaOH, and we do our calculation, and we get 0.00100 moles NaOH. All right. So that was question 3. Now, question 4 asks us to find square brackets NaOH. What does it mean when we have square brackets around NaOH? Concentration. Concentration in what unit? Moles per liter. So we are going to want to have our moles of NaOH over the liters of NaOH. Now, I'll tell you one of the places where people go wrong a lot of the time, okay? Instead of doing that calculation, which is, what kind of a operation are we doing there? That is a division, yes? So when you're finding concentration, you should be doing a division. But a lot of people, because we convert so frequently, they're like, okay, concentration of NaOH. Haha, I have 0.00100 moles of NaOH, and then they go times, and then they're like, what's my conversion factor? And then they start making things up because there is no conversion factor here, because you don't actually want to convert moles into anything. You want moles to just be plugged in on the top. You don't want to convert it into anything. And this is where I get people like, they're just throwing weird numbers together because they want to convert it, because they know that usually we're converting. But remember, when we're doing concentration, we are not converting, not a conversion. Okay, so we're going to do the division instead. We're going to take our 0.00100 moles NaOH, and we're going to divide by our volume of NaOH, which is up here somewhere. Let's go find it. Oh, look, there it is right there. Yes, that is our volume of NaOH, is 10.58 milliliters. Now, do I just want to throw in 10.58 milliliters? It needs to be in liters. So 10, you don't actually have to write this out, but I'm going to write it out down here. 10.58 liters is 0.01058, or sorry, milliliters is 0.0158 liters. So let's not put milliliters in the equation when we want to put liters. 0.01058 liters. 0.001 divided by 0.01058 equals 0.094518. Now, if we look back at our sig figs, we have 4 sig figs here. We have 3 sig figs here.
This is the last call. Any grade 12 classes, please head right now to Gym 1 for a special presentation. Once again, all grade 12 classes, please head to Gym 1 for a special presentation. Thank you.
So we've got 3 sig figs and 4 sig figs, so we want our answer to be to 3 sig figs, so that is going to be 0.0945, and then our unit is molar, moles per liter, NaOH. Okay, and we're going to be looking at a bunch of questions that are like this today. Okay, I was going to say something else, but I can't remember what it was, so it can't have been that important. So we are now going to go on to 7.1D. Yep, and that is on page 19, page 19. So sometimes you're given the concentration and volume of one aqueous substance, substance A, and you're asked to find the concentration of another aqueous substance, substance B. And when this is the case, it is often best to stop converting, just like we did, once you have found moles of B, and then solve for the concentration of B separately, because any stoichiometric calculation, step one is to find the moles of A. Step number two is to find the moles of B. And then in this particular instance, our last step is going to be find the concentration of B, which is a division, not a conversion. So it makes a lot of sense just to kind of stop here and then do the division on a separate line, okay? So you can see we've got our, nowhere on this little chart, does anyone see a box that says molarity or moles over liter? Is there a box that says molarity or moles per liter? Any of them? Mass, number of particles, volume, moles. Anything that says moles per liter in a box? No, and that's because you cannot find moles per liter by converting. You find moles per liter by division, okay? So that's why it's not on the conversion chart. It's not a conversion, it is a division. All right, so we're going to take a look at this example, but this example is almost identical to the one that we just did. Yes? Because look, in our example from yesterday, we had H2C2O4, and here we have H2SO4. In the example from yesterday, we had 2 NaOH, and here we have 2 NaOH. In our example from yesterday, we had a volume and a molarity of the acid, and here we have a volume and a molarity of the acid. If we have volume and molarity, is that substance A or is that substance B? If we have volume and molarity, that's going to be substance Question is, substance A, you should be able to find moles just with the information provided in the question. Substance B, you can't find the moles until you know the moles of A. Can you find moles of H2SO4 just with the information in the question? Yes, you can. So that is substance A. Okay? That's our known. And then our unknown, and you know, this is the other way to do it that's really easy, is to say, oh, look, it says calculate NaOH. That means NaOH is my unknown. That means NaOH must be B. And by process of elimination, you could figure out that H2SO4 is A if NaOH is B. Yes? So we're going to do all the things that we did before. We're going to map our question. We're going to say we're starting with the volume of H2SO4. We're going to find moles of H2SO4, that's moles of A. And then we're going to find moles of NaOH, that's moles of B. And then we're going to stop because we want to find concentration, and concentration is not a conversion, it is a division. Okay? So we do that. Calculation, take your liters, multiply by the moles of H2SO4 per liter, liters cancel out. When we have moles of NaOH and moles of H2SO4, where do those numbers come from? From the coefficients. So we have a 2-to-1 ratio. There are 2, where did it go? 2 NaOHs for every 1 H2SO4. Okay. A lot of people in my third block were kind of skipping this step. They were like finding the moles of H2SO4 and then dividing by liters of NaOH. Okay, you actually have to get to moles of B. You have to find moles of A, and you need to find moles of B so that you can find the concentration of B, right? So we have found our moles of NaOH, and then we're going to divide by our liters. Now, there is another way to show your work for this if you want to show it all in one line. If this confuses you, just pretend I've never said anything, okay? But I can say, okay, I want to start with 0.0156 liters of H2SO4. I'm going to cancel my liters and find moles of H2SO4, and I know that number was given in the question, 0.200. Nice. Now, I still am going to convert to moles of NaOH, so cancel the moles of H2SO4, find the moles of NaOH, that is a 2-to-1 ratio. Nothing different so far, right? It looks identical. The only thing that's different is if you don't want to write the concentration on the next line, if you just want to start and say, I just want to go from scratch and find the concentration all in one line, you can do a division by doing a multiplication. How do you do that? You just put what you want to divide by on the bottom, because we want to divide by it. So that's going to be 0.0250 liters of NaOH. And on the top, I've already found my moles of NaOH. So right now, what I have here is everything has canceled out except for what I wanted. I wanted moles of NaOH over liters of NaOH. I have moles of NaOH over liters of NaOH. So what do I put on the top of that? I just put the number 1. And that makes it a division. Yes? If I want to divide by 2, I can multiply by 1/2. If I want to divide by 0.250, I can multiply by 1 over 0.250. And if that confused you, throw that out and go back to finding your moles of B, and then on a separate line, divide by the moles of B and just pretend I never said anything. But if you like that, feel free to use it. Up to you, okay? Now, we're going to talk about a few vocabulary words now regarding the titration, which was the procedure we did yesterday. Titration is drippy, drippy, swirly, swirly, pink. Okay, drippy, drippy, swirly, swirly, pink. Yes? This is page 20, page 20. Okay? That's okay, no worries. We're good. So that was what we did yesterday. And don't worry if you missed it. We actually have like a little picture that explains kind of what's going on. One lab procedure used to find the concentration of a substance is called titration. It is an effective way to determine the concentration of an aqueous substance. And what we do is we take a precisely measured volume of one solution, and we gradually add another reactant to that until we see a identifiable endpoint. Now, yesterday when we did that demonstration, what was the identifiable endpoint? What did we see that let us know, oh, my reaction is finished? No? Pink. Yes, you were right. See, yeah, you should trust in yourself, okay? Yeah, so how did we know the reaction was over? It was pink, and the only reason that we knew that is because we had added an indicator. So in order to get that identifiable endpoint, we will often add an indicator. There are a few solutions, a few reactions that will self-indicate, like the actual substance itself will change color. But if you remember, what did the oxalic acid look like? Looked like water. What did the NaOH look like? Looked like water. And then we have a salt in water. And what does salt water look like? Water. So had we not added the indicator, we would never know when the reaction was done. It would be like I added water to water and it would look like water and yeah. Okay. So here are a few terms that you need to know. You need to know the term standard. Okay? A standard solution is the one that has a known concentration. So the standard is the known concentration. Is that substance A or is that substance B? That is substance A. There is another word for it. I'm not going to require you to know this. It's in here because I use the same worksheet in grade 12. It's called the titrant, but we're going to put like a little black diamond beside that because that's a lot of words to learn all at once. Might as well just learn that it's the standard. Okay. The other thing is going to be our sample, and that's the one where we do not know the concentration. It is an unknown concentration. And so that would be substance B. Okay. Now, if you think about it, I've taken a sample of some water and maybe I want to titrate it to find its concentration. So that's where the term sample comes from. I take a sample of some acid. I've got a big vat of, we had a big vat of that NaOH and I took a sample of it to titrate it. It's also known as the analyte because it is the thing that we are analyzing. But again, that is a black diamond term. You do not need to know that this year, okay? You need to know the term burette. What does the burette look like? It looks almost like a pen. It's big and long. It's got that stopcock at the bottom, and you drippy from it, and swirly, and yeah, okay. Pink. The indicator is the thing that changes color, and it changes color to let you know that the reaction is finished. Now, the indicator that we used yesterday was called, and this is such a great word, I love it so much, phenolphthalein. Okay, it's got a PHTH in the middle of it. It always makes me think of Sylvester the Pussycat because it's got phenolphthalein. Okay, we don't actually say it like that. We say phenolphthalein. The PH is silent, but it's so much fun. Okay. Now, there is another word here, and that is called the equivalence point. This is also known as the, AKA, the stoichiometric point. And it is the point where the reaction is perfectly complete. There's no extra acid, there's no extra base. I've reacted exactly one of those with exactly two of those, and all I've got is products. I don't have any left over of either reactant. Okay? So it is where substance A and B have completely reacted, and there's no leftover of either reactant. That's our equivalence point. I didn't do this with the other class. I need to do that on Monday. I'm like, what happened? Where did this go? The end point is the point where the indicator changes color. Now, you may think, well, the end point should be the equivalence point, right? Like I should see that color change when the reaction is perfectly complete. And if you choose your indicator well, which in grade 12 you'll get to do, okay, your endpoint should happen at the same volume as the equivalence point. It should happen at the same time, okay? But the endpoint is specifically when the indicator changes color. Sometimes, if you choose a bad indicator, it might change color way before all the reaction is complete, right? Or it may change way after the reaction is complete and you've added way more of it. And yeah, but that's a grade 12 problem. That's not a U problem, okay? And then finally, we have an outlier. And an outlier is a titration value. Normally, you know how last day I just did one? Like I took one sample and I titrated and I'm like, here's my volume, let's go calculate it. Normally, when you're doing an experiment, you know your data is not going to be perfect, right? You know that. One way to make your data better is to repeat it, and to repeat it several times, yes? And if you can get those, like let's say I did this several times, and in this one I got 10.85 milliliters. The next time when I titrated it, I get 10.87 milliliters. That's quite close, right? 85, 87, right? What if I titrated it and I got 13.8 milliliters? And all my other values were really close to 10.85. I would know that I did something wrong there, yes? And for the purposes of chemistry 11, what we found is that if you have something that is further than 0.2 milliliters from all the other data, you can call that an outlier, okay? And you can throw it out of your calculations, okay? So here's our process of titration. Last day, we actually did a bit of what we call a reverse titration, where our unknown concentration was in the burette and the known substance was in the flask. But normally, and this is what you are going to do next week, your standard, what is a standard? It's the one where it is known, that is substance A. Substance A normally goes in the burette, whereas substance B normally goes in the, what do we call this? It's a flask. What kind of flask? It's an Erlenmeyer flask. Erlenmeyer flask. Okay? So normally the sample goes in the Erlenmeyer flask. So that is substance E. And the other thing that goes in the Erlenmeyer flask is the indicator, yes. So basically at that point, we drippy, drippy, swirly, swirly. And we don't just do it once, we repeat it until at least 3 volumes are within 0.2 milliliters of each other. Yes? So that might take 3 trials, it might take 4 trials, it might take 5 trials. You are going to have a big long block to do this in. Normally people can finish it within a normal size block, so you'll have tons of time to, like, you know, be as perfectionistic as you want. That will not be a luxury you have very often, so enjoy it, okay? Any volumes that are not within that limit are the outliers, and when we do our calculations, we're going to exclude any volumes that are not within 0.2 mils of each other. We will exclude the outliers. And then finally, once we've done all the lab work, we're going to do the stoichiometric calculations. And remember, what is step one of any stoichiometric calculation? Find moles of A. Second step is find moles of B. And then step three in a titration is going to be find the concentration of B by taking the moles of B and dividing by the liters of B. So all the questions in this worksheet are going to be using this strategy here, okay? Now, this next little section is probably more useful if you hadn't seen the live demonstration yesterday. But if you forget, if you're like, I don't remember, how did it go? What did we do? You can look at this and you can be like, oh, okay, what did we do? We measured out some acid using a pipette. Where did we put it? We put it into an Erlenmeyer flask. What did we do with the burette? We filled the burette with the sodium hydroxide solution, and while we were there, what did we do? We measured the initial volume, okay? Now, the other thing we needed to do with our Erlenmeyer flask is we needed to add some dye into it, so this is now HCl plus indicator, okay? And now we drip and swirl, yes? And we see a color change. And once we see the color change, we record our final volume. And then the calculations here are exactly like the calculations we did earlier today. We took the final volume minus the initial volume, and that is the volume of NaOH used. And we already know the concentration of NaOH because that is that the sample or is that the standard? The one that we know the concentration. That's the standard. Is that A or is it B? That is A, okay. All right, and now what we're gonna do is we're gonna take all that information that we had on the previous page, we're gonna say we know that we had 10 mils of the HCl because we used our pipette. We know we had 12.71 mils of the NaOH because we calculated that final volume minus initial volume. We know the concentration of the NaOH because it was given in the question. You guys are going to know the concentration of the NaOH when you do your experiment because guess what? You just calculated it either yesterday or today, right? So this is substance A here. This is substance B. You're going to find the moles of A. Then you're going to find the moles of B. And then on a separate line, you're going to do the division. One thing you don't want to do is you don't want to put equals moles and then put divided by liters. Because what you're doing is you're saying, maybe you're saying, that would be like saying 6 times 3 is equal to 18 divided by 2. Right? Can you do that? No, because it's not equal. So if you have calculated the moles, just leave it alone, and on your and then on a separate line you could say, now I want to do 18 divided by 3 or whatever, 2. Okay, on a separate line, because otherwise if you do it in the same line it won't be equal anymore. Okay. Now we have some exercises here. Just before I set you free on those, I did want to take a look at page 24, question number 5, because this is what some actual data will look like, okay? And one of the things that people usually miss is that the concentration of the NOH is given to you here. They're like, where's the concentration of the NOH? And they can't find it, but it's given right in that top corner. So don't lose track of that. You are given the concentration of the NaOH. And you'll notice, how many trials are there here? There's 4 trials, yes? 4 trials. So you're going to have to decide, are there any outliers when you calculate your average volume of the NaOH delivered? Which ones are you going to include in that average? You're going to be identifying who is the standard, who is the sample. You're going to be calculating the whole shebang. The answers are down here. The worked answers are in the key. I think this should have only 3 sig figs. Oops. Okay, 6. But you'll take a look at it and you'll be like, oh, it should have only 3 sig figs, Miss Spence. And I'll be like, oh yeah, shoot. Okay. So your homework then is to do pages 22 to 24 in the blue book. And you're going to be also doing pages 22 to 24 in the blue, and pages 108 to 111 in the ivory book. That is some more practice with enthalpy and with exothermic and endothermic. This one we're going to have a quiz on Tuesday. Okay, so on Tuesday, June the 13th, there's going to be a quiz on enthalpy. It will be very short quiz. Okay, just enough to make sure that you kind of know what you're doing. Stoichiometry quiz, that's going to be on section 7.1. We've done almost all of it. We need to throw in particles and gases, but you already know how to do moles of particles and gases, so it's just like throwing a different conversion at the beginning or end. So that's going to be on Wednesday. Okay. For the rest of the week, when we're not doing that, we're going to learn a little bit, so small amount, about limiting reactants. And that's when, if you have a reaction, it's when you actually do put in more of one reactant than will react with the other one. And so you have a leftover of one reactant, and you get the other one is all used up, and figuring out which one has a leftover and how much and all that kind of stuff, which is like fun things. If we had one more week, I'd be able to complete this course properly, but we don't, so there we are. Okay? Yeah. Yeah. It's, yeah, I mean, for the quiz itself, it's all of section 7 point, or 6.4, except for the very last one, because the bond enthalpy. So yeah, like all of this stuff, yeah. Yeah. The only reason I have them is so I can make little corrections in them. That one. You can borrow. I know you were like, oh, I can't work, darn. I forgot my books today. Oh no. There you go. I'll be right with you. Yeah. That should be 6.4B. I don't know why it says 6.5. Yes. Oh, the pages. I'm so sorry. I will write this out because we can get rid of this now. I'll be right back with you. It was pages 22 to 24 in blue and 108 to 111 in ivory. Yeah. And the charge of NO3. I need to fix that. Is today Friday? I'm sorry, I missed that. Yeah, yeah. Oh, right? Yeah, yeah, yeah. Yeah, yeah, Your other completely optional homework assignment is to look up Smooth Criminal Slap Bass and go watch the video on YouTube. It's just really good music, and I would highly recommend it. Okay. I was listening to it again this morning, like I found it like a couple months ago, and I just came across it again today, and I'm like, oh, that is really good. So yeah, I would highly recommend it. 2 minutes of your life.